For the first video in this unit, we're going to take a look at two topics, 7.1 and 7.2, Introduction to Air Pollution and Photochemical Smog. Air pollution is defined as the substances present in the atmosphere that, when concentrations are high enough, they have the potential to harm living things, affect the way that ecosystems function, or damage human-made structures such as buildings, bridges, and roads. Air pollutants can come in the form of chemical compounds, particulate matter like dust or smoke, or even living things like mold. Air pollutants can exist in many layers of the Earth's atmosphere, but we generally use the term air pollution to refer to that which is found in the troposphere, the lowest layer, which is where living things, like us, are found. Air pollution occurs both naturally and as a result of human activity. This table illustrates the most common and most important to know about air pollutants. Sulfur dioxide, SO2, is a gas that comes mainly from the combustion of fossil fuels like oil and especially coal. Not only does it irritate the lungs, but it can also damage plant tissues as well. It is especially damaging to people who have respiratory ailments such as asthma, and reacts with water in the atmosphere to form sulfuric acid, a component of acid rain which will be studied later in this unit. Nitrogen compounds like nitrogen oxide, NO, and nitrogen dioxide, NO2, are the result of combustion reactions. While nitrogen oxide is colorless and odorless, nitrogen dioxide is a reddish-brown stinky gas. Nitrogen oxides are respiratory irritants and contribute both to acid rain and the formation of photochemical smog, a topic later in this presentation. Carbon monoxide, CO, is a colorless, odorless gas that is formed by incomplete combustion. It is therefore a common vehicle emission and can be very dangerous as an indoor air pollutant where there is poor ventilation and people cooking indoors with biomass like charcoal and manure. Carbon monoxide is hazardous because of its ability to displace oxygen in binding to the hemoglobin in red blood cells. Particulate matter is the result of combustion as well as activities that kick up dust and other particles into the air. Not only does it reduce visibility in the air, it can also make respiratory and cardiovascular disease worse. We'll take a look at particulate matter in a bit more detail in a few moments. Lead is a naturally occurring trace metal found in rock and soil. It is released into the atmosphere when oil and coal are combusted and, for a long time, was a component of gasoline because it improved a car's performance. Additionally, lead was an ingredient in paint which, when peeled off and ingested, especially by young children, can lead to nervous system damage. Although leaded gasoline and paint are banned in the United States, leaded gasoline is still used in a handful of countries, and leaded paint is still commonly found in developing nations. Like lead, mercury is another metal found in trace amounts in oil and coal. So, when they are combusted, mercury is aerosolized and released into the atmosphere. In the next unit, we will study how toxins like mercury accumulate in the bodies of organisms found higher up in food chains. Ozone is a molecule comprised of 3 oxygen atoms. It is formed by chemical reactions in the atmosphere and not only is hazardous to the health of respiratory organs in animals and damaging to plant tissues, it also reacts with plastic and rubber, degrading it over time. Volatile organic compounds, or VOCs, are a broad category of hydrocarbon molecules. Included are things such as gasoline, oil-based paints, some cleaning products, as well as the natural emissions of some types of plants. VOCs are significant as an ingredient necessary for the formation of photochemical smog. The final pollutant is a familiar one, carbon dioxide. A product of all combustion reactions, although it has a negligible effect on health directly, it is a contributor to global climate change since it is a greenhouse gas. Particulate matter, abbreviated PM, is the collection of solid or liquid particles that are suspended in air. It results from the combustion of biomass fuels, fossil fuel combustion, road dust kicked up by vehicles, and from naturally occurring sources like forest fires and volcanic eruptions. Particulate matter is classified based on the size of the particles, which this model helps to illustrate. To gain a better perspective on the size of particulate matter, notice that the diameter of a typical human hair ranges between 50 and 100 micrometers, the size of the largest circle shown. Particles ranging in size from 10 micrometers to 2.5 micrometers in diameter are called particulate matter 10, or PM10. Particles smaller than 10 micrometers are of concern because they are too small to be filtered out by the nose and throat and can end up deep within respiratory organs. Particles of 2.5 micrometers and smaller, called PM2.5, are an even more serious health concern, not only because their small size allows them to travel even farther into the respiratory tract, but because they tend to be made up of substances that are more toxic than particles that are larger. Reduced visibility, or haze, is largely attributed to particulate matter, and when enough is present, such as due to a large volcanic eruption or a substantial forest fire, it can block sunlight to the point where a plant's ability to photosynthesize is diminished. Primary pollutants are substances that are released directly into the atmosphere, either due to a human activity or natural event. They include things like carbon monoxide, carbon dioxide, sulfur dioxide, nitrogen oxides, particulates, and many kinds of volatile organic compounds. Once in the environment, some kinds of primary pollutants participate in chemical reactions to form secondary pollutants. For example, sulfur and nitrogen compounds react with water to form sulfuric acid and nitric acid, respectively. Both oxygen and sunlight are involved in the chemical reactions that result in ozone formation and photochemical smog, something we'll learn more about later on in this video. Because of the way in which they're formed, controlling secondary pollutants requires the consideration and control of the primary pollutants that create them. For example, rather than trying to reduce ozone pollution directly, it would be more effective to combat the sources of the primary pollutants, like nitrogen oxides and VOCs, that are necessary for its formation. It is important to recognize that natural processes and events also result in air pollution. However, most of our attention is focused on human-caused pollution since not only are they more significant in the atmosphere in many cases, we have the power to influence its formation. Forest fires release carbon monoxide and dioxide, particulate matter, and nitrogen oxides. Volcanic eruptions, also responsible for those pollutants, also release sulfur dioxide. When lightning rapidly heats the air surrounding it, it splits nitrogen gas and oxygen gas apart. Individual oxygen atoms are then free to react with other oxygen gas molecules, forming ozone. Even plants are responsible for producing some pollutants. They release a variety of VOCs, some of which you may recognize as the odor coming from pine trees, other conifers, and citrus. Anthropogenic sources of pollutants include the combustion of fossil fuels, both in electricity generation and as fuels for transportation, industrial processes like steel production, and solid waste disposal. These graphs quantify the amount of 4 major pollutants released into the atmosphere annually. For carbon monoxide, Nearly all of the emissions are exclusively the result of human activities. The same can be said of nitrogen oxide emissions. Only fires, most of which are naturally occurring, contribute to natural emissions of carbon monoxide and nitrogen oxides. Sulfur dioxide emissions, on the other hand, are virtually all attributable to anthropogenic sources. The smallest particulate matter, PM2.5, is the result of human activities, but also naturally occurring processes such as fire and wind, included in the miscellaneous category, that can kick up dust and blow it around in the atmosphere. Historically, the term smog was used to describe a combination of smoke and fog. The definition has expanded to include specific types such as photochemical smog. A number of pollutants are involved in the creation of this secondary pollutant, but we still don't have a full understanding of the chemical processes involved. To form photochemical smog, two chemical compounds are required: nitrogen dioxide and volatile organic compounds. In the bottom half of this model, we can see that nitrogen dioxide is broken down into nitrogen oxide and a free oxygen atom. The free oxygen atom can react with oxygen gas in the atmosphere to form ozone, and the nitrogen oxide reacts with VOCs to form photochemical oxidants. It is this combination of ozone and photochemical oxidants that comprise photochemical smog. The top portion of this model demonstrates that, with little to no VOCs, nitrogen dioxide contributes to the formation of ozone during the day when light is available, but breaks down at night when there isn't any light. Other factors, such as cloud cover that blocks light and temperature, influence the rate and quantity of photochemical smog formation. For example, the rate of naturally occurring emissions of VOCs from plants increases with temperature. Although efforts to reduce photochemical smog have seen some success, it is still a problem in many cities around the world. It is harmful to human health in a variety of ways. It is a respiratory irritant, potentially painfully so, leading to throat irritation, difficulty breathing, inflammation of the lungs, and can exacerbate problems like asthma and COPD, chronic obstructive pulmonary disorder. In some people, it can trigger headaches, and evidence exists as to its connection to increased risk of heart damage and heart attacks. Since nitrogen oxides are required for the formation of photochemical smog, and a significant source of nitrogen oxides is automobile exhaust, the use of a pollution control device called a catalytic converter was mandated on automobiles beginning in 1975. To learn about how a catalytic converter works, click on the link above to view a short video that will explain more. In 1963, one of the first major environmental laws was passed in the United States. Since then, it has been amended 5 times in 1965, 67, 1970, 77, and 1990. With each amendment came new regulations and/or requirements for pollution control. In some cases, state and local governments have enacted extensions to the Clean Air Act to close loopholes or supplement gaps in the federal legislation. Initially geared for reducing the pollution resulting from the growth of automobile use in the 1950s and 60s, the amendments helped to expand efforts aimed at reducing other atmospheric pollutions such as acid rain and airborne toxins. The Clean Air Act is widely regarded to be a successful piece of environmental legislation. It has directly resulted in the reduction of pollutants like lead, sulfur dioxide, particulate matter, ozone, and nitrogen oxides. Researchers have also demonstrated the indirect benefits of the Clean Air Act and estimated that as of 2020, since its implementation nearly 60 years ago, It has prevented nearly 5.5 million days of school lost and 17 million lost workdays due to health issues caused or made worse by air pollution. In addition, even though the total cost to enforce the Clean Air Act standards exceeds $500 billion, an estimated economic savings of $50 trillion has resulted by preventing health problems as well as damage to structures. Since the 1990s, the Act has contributed to a 60% decline in pollution from the manufacturing industry. And since the 1980s, there has been a reduction of ozone by 25%, atmospheric mercury by 80%, and atmospheric lead by 90%. Thanks so much for watching. Take care.